Hi. This mini lecture will concern with forces between bodies in contact with each other. This discussion will assume that we're dealing with bodies whose length scales are greater than nanometers. This is an example of an object that's called macroscopic, and it contains trillions and trillions of atoms. As you know, forces quantify interactions between bodies. Some forces can act over a very long distance. Example of such a force is a gravitational force, or for instance magnetic force. And these kinds of forces can act over distances that are much greater than the sizes of the bodies that are interacting. On the other hand, other forces require a direct contact. Now, whenever two macroscopic bodies interact by direct contact, in other words by touching of their surfaces, we describe such interaction in terms of contact forces. To be more precise, a contact force is a force that arises only when the separation between macroscopic bodies is comparable to atomic dimensions. When a body rests or slides on a surface, that surface exerts a contact force on the body. So for instance, here is a block resting on an inclined plane. It's a classic example. And it experiences two forces. One is the weight, which is the gravitational force with which the Earth pulls on the block. And the other is the contact force with which the surface acts on this block. We can resolve this contact force into two components, one perpendicular to the surface and another component parallel to the surface. This perpendicular component is called the normal force. Normal means perpendicular. And this parallel component is the friction force. For an object that's not moving relative to the surface on which it's resting, this is an example of a static friction force. The role of the static friction force is to prevent this object from sliding down the inclined plane as pulled by this component of the weight. Incidentally, the role of the normal force is to prevent the object from going through the surface because it's also acted upon by this component of the weight. Now, on a microscopic level, contact forces result from the interatomic interactions between the atoms in the two contacting surfaces. And fundamentally, these types of interactions are electrical or electromagnetic in nature, as all chemical interactions are. It deserves to mention that the strength of friction forces depends on the roughness of surfaces in contact, which is a pretty intuitive idea. But what's interesting is that smoothing the surfaces can actually increase the friction, since more atoms or molecules are able to interact and bond. So it requires a greater external force in order to break those more numerous bonds that form between smoother surfaces. It's important to make a distinction between a kinetic friction force, which forms between contacting surfaces that are moving relative to each other, versus a static friction force that forms between contacting surfaces that have no relative motion. I'm going to focus on the static friction force between kinetic, because kinetic friction forces are a story in its own right. They have to do with energy dissipation. So to focus on the further exploration of static friction forces, we're going to perform a simple tabletop experiment. So here's a metallic container, I call it cradle, with a spring attached. I'm going to place it on the table. And I'm going to wait with a book. I'm going to wait with a book. And the reason I'm going to pull it through a spring and not through a string is because the extension of the spring is an indicator, a relative indicator of the largeness of the force with which I'm pulling, because we know that the larger is the force exerted on the spring, the more extended it is. So as the spring is extended, we see that I'm applying a larger force, extending, applying larger force, but the object remains static up until about now. And then the object starts slipping. So let's analyze this more quantitatively. So here's a free body diagram for the situation. Weight, normal force, static friction force, and the applied force. And we saw that for applied force that's below a certain threshold value, static friction force must have adjusted itself such that it's equal in magnitude to the applied force and opposite in direction. Otherwise, there would not be a force balance and this cradle would move. So in other words, if I plot the magnitude of the static friction force, magnitude, hence no arrows, versus the magnitude of the applied force, the magnitude of the static friction force equals to the magnitude of the applied force up until a certain point. The maximal value, there exists a maximal value of the static friction force, which I'm going to label Fs star. And if I apply external force that's greater than Fs star, the maximal value of the static friction force, then the object slips and now it experiences kinetic friction force, which in general is smaller than the maximal value of the static friction force. And that's why it's harder to get an object to move than to maintain its state of motion once it's already moving. So what happens is it took a certain critical force in order to break the bonds, the weak bonds that form between the surfaces, or in some cases it's not the chemical bonds that we're breaking, but we're breaking through micro roughnesses, little valleys and hills in the micro roughness. It takes a certain amount of critical force to break through. It turns out that for macroscopic objects there exists an empirical relationship, an empirical proportionality between the maximal value of the static friction force and the normal force acting on the body. And the constant of proportionality is called the coefficient of static friction. And it's this coefficient is what contains the interesting physics, such as the nature of chemical interaction and the dependence on surface roughness. Having said all this, we're going to look at a practical calculation, a simple practical calculation. We know that some streets in San Francisco are very steep. For instance, the steepest streets are Filbert Street and 22nd Street with 17.5-degree incline, although it certainly feels much steeper when you drive on them. So if I park my car on those streets, at what angle, how close am I to slipping? Right? Well, in other words, if I could control the angle of the street, at what angle would it slip compared to 17.5 degrees? If the car is not slipping, that means there's a static situation, so the sum of the forces equals to 0. Let me break this up into two components. X, which is along the surface, I have a balance between the static friction force and this component of the weight. And Y, I have a balance between the normal force and the other component of the weight. I'm going to divide these two equations. So what happens is that as I increase the angle, this component of the weight increases, just like my pulling force, and the static friction force is able to adjust itself. But that happens up until a certain point. And we know that that critical point is Fs star, corresponding to a critical angle theta star, and we saw that Fs star over n is the coefficient of static friction. So I have this. Coefficient of static friction is the tangent of the slippage angle, which is how you can, in fact, measure the coefficient of static friction. So it turns out that for rubber on concrete in dry conditions, μs is about 1. So that corresponds to 45 degrees. So we're safe. But in wet conditions, theta star turns out to be very close to 17.5 degrees. So it's actually not that safe to park or especially drive on those portions of those streets in wet conditions. So we've made some practical prediction using these simple ideas. In summary, friction force is a component of the contact force between objects that resists relative motion between these objects. In static conditions, the friction force is able to adjust itself until a certain point. Right at the point of slippage, there is an approximate relationship for macroscopic bodies that says that the maximum value of the static friction force is equal to the coefficient of static friction times the normal force. And the property of this coefficient depends on surface roughness and the nature of chemical interaction between surfaces. One has to be more careful when dealing with non-macroscopic objects. Clearly, we cannot talk about friction forces between two atoms in contact. So the concept of friction is an emergent concept. It's an idea that arises when dealing with macroscopic objects with many atoms. So at what length scales can we start talking about friction as we increase the size of an object? So I'll leave you with this fascinating frontier question. Thank you.